Welcome everybody for the lecture 7. So in the first half we have seen the AI models for infrastructure part 1, and now we will go for part 2. And I think before we start in part 2, you will see some of the information we are going to discuss, like PyTorch and those kind of techniques. So tomorrow we will be solving one whole problem by using that PyTorch as well as the CNN. So what I will ask you, whatever we discussed today, if you can go back and open your math work and try to practice some of the PyTorch or CNN problem. So tomorrow it will be easy for everybody to kind of how to model that, or how to code that accordingly. And as I said that I will be showing you the details in the MATLAB, but if you are comfortable in Python, you can actually do Python as well. Okay. So in the today's discussion or the today's lecture, we are going to talk about, as I said, that some of the introduction of advanced AI technologies. We will also talk about deep learning and reinforcement learning, and these models we are going to actually discuss in terms of the application of infrastructure monitoring. We'll also talk about the conventional neural network as well as the physics-informed deep learning. So now let's start with the SVM. We have seen the details of the SVM in the first part. So if you quickly look into that, remember that what we have talked about. So SVM, as I said, is one of the most widely used supervised machine learning technique, and they are particularly well known for their solving the complex problems, non-linear problems, using relatively small data sets. When you have small data sets, then you can use this SVM. And now let's try to understand their key characteristics, including their strength, their weakness, and some of the examples of their effective use. Okay. So now let's first see what is their strength, and following that we will see some of the weakness. So the strength of the SVM, as I said, that is the efficiency with the smaller data sets. So unlike some other algorithms, like if you think about artificial neural network, which is ANN, SVM does not require a large amount of data to start producing the meaningful results. So if you have a very small data set also, you can still work with the SVM. And another important factor is that in fact SVM is designed effectively such a way to handle data with high degrees of uncertainty and heterogeneity. So if you have a lot of uncertainty in your data, I think SVM is another good option to use that. And that makes it versatile for different types of problems. You can actually use SVM in heterogeneous, different kind of problems. And another very good SVM is that its computational efficiency. That means the speed. So SVM classifiers, once they are trained properly, typically they run at a good speed, okay, and are very computationally efficient compared to the many other machine learning models. So to summarize, if you will see that the SVM combines the robust performance, good generalization ability, efficient computation, as we say, and they can actually work with a limited number of data. So you don't need a large data sets to create a SVM model. Okay. So now we are talking about a lot of strength, and then now let's see what are the weakness of SVM. So as we said that every tool has some kind of limitations or some kind of weakness. So SVM also, they do have their own challenges. First, it behaves like a black box approach. Okay. That means that the intrinsic relationship between the input and output are not always transparent. Okay. So in other words, we cannot always easily interpret why the model made in a certain decision. So whatever is happening inside the model, sometimes it is even difficult to interpret. And another important limitation of this SVM is that they have limited tolerance of noisy data or outliers. If your data does, if the data do have a lot of noise, or if your data do have a lot of outliers, then it could be tricky to use this SVM, or data with missing values. So those kind of cases, SVM can be little tricky, which can degrade actually your performance. If you have a lot of noise, if you have a lot of missing data in your, because we are dealing with not dealing with a large data sets, we're dealing with a small number of data sets, so we have to be little concerned about those perspectives. And then SVM can also be susceptible to overfitting. So overfitting is also another concern with this SVM, especially when the model is not tuned correctly, or if the data set contains many kind of irrelevant features or many kind of uncertainties. That's the period it can have some kind of overfitting. And these are the weaknesses which underline the importance of carefully pre-processing your model and selecting the model using your SVM. And now if you will try to look into one of the example. So the example of the SVM could be one of the great example is the energy sector. So load and demand forecasting, which is very, very essential for the energy management. So you can see that SVM can consistently perform very well in those kind of sectors. In many forecast scenario, you can also see that SVM techniques have yielded lower mean absolute percentage error very well, and compared to the other methods, including the neural networks as well. And why that actually happens? Because the SVMs emphasize, they mainly work on empirical risk mitigation. If you remember, we have talked about this in the morning, that they emphasize a lot about ERM, which is the empirical risk minimization, rather than relying on the predefined expert rules, something like what ANN does. So that actually helps the SVM models to achieve very highly accurate forecast in relatively very short period of time, with relatively very short number of data. So you can see that this means that the energy companies, they can actually predict the demand more reliably, they can predict the demand more fast, allocate the resources more efficiently, and ultimately that can also help to reduce the cost. So basically you can see this SVM actually represent a very powerful machine learning technique with several advantages, as we said, particularly their effectiveness with small data and their strong performance in the real life scenarios like energy forecasting or many other cases. However, as we said, they do also have some kind of limitations. So when you choose carefully, you have to be tune this SVM very carefully. And SVM can be consistent technique in a lot of AI applications, especially the advanced AI applications, which is in the infrastructure monitoring. Both it helps for the accuracy as well as the efficiency. Okay. Now, similar way, we have talked about RF in the morning, if you remember that, which is nothing but random forest, right? So now we will similar way we will try to look into their strength, their weakness, and one example. So as we said that in the morning, that the reinforcement, the random forest is a versatile model, and that assemble learning technique based on the decision trees. So instead of relying on as a single tree, it actually builds the multiple tree. I think if you remember that. So now let's quickly talk about their strength fast. So these kind of models are known for their flexibility. These kind of models are known for their robustness. They can handle a wide range of data varieties like binary, categorical, numerical, lots of type of features they can actually handle without the need of extensive pre-processing. So unlike many other methods, these models actually don't require the data to be rescaled or the data to be transformed, which saves a lot of time during the data processing. Okay. And another very great advantage of this kind of model is their ability to handle noisy data sets compared to the previous ones. If you have a noise in your data set, if you have a missing value of your data set, then random forest is a very good method or the model to use it. And RFs are less prone to overfitting compared to the previous one, and especially compared to the single decision tree. So they are very good if you have noise in your data. They are very good if you have a lot of missing data in your data set as well. And they are also kind of very good because they are not prone to much overfitting. Okay. So as we say that they are always better than considering one single decision tree. So they are also very faster tree-based technique as well. That means they also save a lot of computational time. That makes them very ideal if you want to get your result very quickly and very fast. So in short, you can say this RF combines the ease of use of high performance. They makes it one at a go method in machine learning. But when we talk about a lot of strengths and benefits, then we do also understand that they do have some limitations as well. So when we talk about the limitation of this random forest, the random forest is not perfect, as we say. Like SVM, it is often considered also as a black box model. That means the internal decision making process is sometimes little difficult to interpret. So you are giving the input, you are getting the output, but what is happening inside the model, that can sometimes behave as a black box. So you may not know that why that kind of decision has been taken or why that kind of prediction has been done. Sometimes it could be work as a black box, right? So although you can say that the RFs are typically very efficient, their execution time can grow significantly with a very large data set. So they are very good with large data sets as more because we have more decision trees, more data points also required for greater computational effect as well. Additionally, this kind of models for large data sets can also consume a lot of memory, okay? Because we are dealing with a lot of data sets, which can become a bottleneck for systems with limited resources. So you need to use some kind of HPC or some kind of cloud to use this kind of model. So basically RF excels at accuracy and as well as robustness, but it not be the first choice if you talk about the ultra large scale data or resources which constrain environments with some kind of optimization. So now if you will try to look into one of the example here, one of the example of random forest is another is that the modeling the travel mode choice. So that if you will try to take the example like that, you can see that how this RF has outperformed many other machine learning, especially when we have classifications in this area. So as we said that the high accuracy of tree-based SML classifiers is very good and is largely due to their flexibility gained by combining multiple decision trees. And this flexibility is especially valuable when you think about modeling the complex human behavior, such as people's choice of the mode of transportation, people's choice of mode of any kind of decision. So those are when we kind of think on that example, this RF is very good model to use those. So the dominance of RF over the other tree-based classifiers stems from its diversity of learned the trees, because it is a very direct result of its randomized picking. If you remember that we consider different kind of decision trees and they all kind of take different type of data, and ultimately you combine it together and get a very good output which gives you a better result. So you can understand that these methods are very powerful, they are very versatile, they are very kind of robust machine learning model, and minimal preprocessing tolerance for noisy and missing data, so their resistance to overfitting as well, which actually makes them a very excellent choice when you think about wide varieties of problems. Definitely they do have their weakness as well, as you said, they are highly computational and memory demands when you deal with the large kind of data sets, right, and limited interpretability. So this RF actually kind of deliver highly accurate, flexible and scalable solutions, as demonstrated from the you can think about success of modeling travel mode choice or people's choice. So basically in these kind of cases or applications, RF actually works really good. Now another important one is the k-means as well. We have also seen the basic definition and relevance of k-means, as we said that k-means also is one of the most widely used clustering algorithm in machine learning. Unlike SVM or random forest, which are typically used for the supervised learning task, k-means is not supervised, it's an unsupervised based method, meaning that it groups the data without the predefined level. So you are not defining the level in the case of k-means compared to the SVM or the random forest, right? It is popular because it is very speedy, it is popular because it has a very good scalability and simplicity. So now if you will try to quickly look into their strength, weakness, and we'll also kind of see one of the example. So when we talk about k-means is very prized for being scalable, it is very good for being rapid, and it is very straightforward model compared to many other unsupervised models. So it can efficiently handle again the large quantities of data, which makes it very suited for the big data context. It's very simple iterative process or approach, and assigns points to cluster and updating the centroids. Means that it can cover it very quickly, it can produce the interpreted or interpretable cluster assignments very fast. And another very good advantage of this kind of models are that they can be implemented as I said, very easily. They can be integrated into pipeline with minimal computational overhead. So you can also save some computational cost as well. In short, it's a very go-to choice for quick and effective clustering when you have a very large data sets, right? But when we talk about a lot of strengths, lot of advantages, we do understand that it will also come with some kind of limitations. And k-means they do have their own limitations, and they do bring some kind of challenges as well. So one of the very big limitation of this k-mean is they are highly sensitive to initialization. That means that the way the cluster centroids are first chosen are significantly affect the final outcome, and sometimes they can also lead to some suboptimal clustering. So that's one of the limitation of this. And another limitation of this kind of model is that the user must specify the number of cluster. That means the number of k they are considering in the model at a very advanced stage, right? That means it's not always obvious in the real world data. Choosing the wrong k can actually distort the whole model's output. So you have to actually define the number of k's at a very advanced stage. And then also k-means struggle with the non-convex cluster as well, or data sets as well, which have some kind of irregular shapes. As the algorithm inherently assume the clusters, and if you remember yesterday, they has to be spherical. That's what k-means actually consider, and they are always even in size, if you remember from yesterday's slide. that is actually one of the weakness which K-brains miss, because in the real life world it can never be possible, right? Now you will try to take one of the example here. So you can see that if you think about K-means applied to a vehicular ad hoc network, which is being also called as a VNETs, which is been VNETs, and that we kind of can do for data congestion control. So in a scenario for this kind of cases, you can see that this kind of clustering can use to group the messages and control the unit, then determine the parameter for each of the clusters. And these parameters then they were sent directly to the vehicle waiting at the intersection, right? So by clustering of data intelligently, you can see that the system can able to reduce the the packet loss ratio or average delay or collision probability. Those kind of things can be taken care of. So basically, if you will look into the strength and weakness and some kind of example, you can see that they are very fast, they are very simple, they are scalable and supervised learning technique, and that can excel in grouping the large data sets. You can deal with the large data sets. So they do have some limitations, like they're sensitive to the initialization, they need to predefine their cluster number in very advanced, they're difficult with the non-complex cluster, which must be carefully managed when we are talking about the real life data. And when applied thoughtfully, especially for the case of this VANT's configuration, you can see that K-means can deliver a very substantial performance improvements for these cases, and they can actually be enabled to innovative solution for complex problems, especially when you have big data and those things, okay? And now another important, the term which we use a lot in the machine learning, or when we talk about the AI-inspired cases, and that is being called as a deep learning, right? So what is deep learning? I think we have seen a little bit of introduction. So deep learning has actually emerged as a breakthrough in tackling problems which involves a very large quantities of data. So that's the time when we use the deep learning quite a lot, where traditional machine learning actually struggles. Especially with the high dimension, when you have a lot of noisy data, or deep learning actually is good in those kind of cases. So you have seen that the deep learning actually can achieve a tremendous success in tasks such as image classification, or natural language processing, speech recognition. So those are the places actually deep learning is a very good example to use it. And it is the ability to handle complexity and the scale that sets the deep learning apart compared to the other available machine learning models, okay? So if you will try to see or look into the deep learning network, so what we exactly mean by deep learning network? At the core, deep learning lies at the deep learning neural network, which we also call as an DNN, right? So to understand a DNN, you have to understand a very simple concept which is artificially neural network, which is being called as an ANN. So an ANN is loosely inspired by the biological neural network, if you remember that. It consists of a layer of interconnected nodes or neurons, which is designed to process the input data and produce an output, right? That's how it works. And typically, if you are looking to the ANN, so this is some way it could possibly look like. I think you all must be aware of how the ANN will look like, right? So now if you will try to understand, that's how ANN will look like. And now if you will think about what is the tradition of ANN, an input layer where the data enters in the network, right? And one or two hidden layers will be there where the computation actually happens in the ANN. And then there is an output layer for the ANN which produces the prediction or classification, right? If you look back into this particular case, right? And that's how generally ANN works. While ANN can handle a very straightforward task like solving the mathematical equations or mathematical questions or simple computer problems, they are not good with the complex problems. They are not good with the high dimensional tasks such as image recognition or something kind of natural language processing or computer questions. They are not good in dealing with those, and that's the reason we have kind of moved from ANN to the DNN, which is called as a deep neural network, okay? So to address this more demanding problems, we run into the deep neural network. So DNN is then extended, you can say, the concept of ANN by introducing many more hidden layers and giving them a greater depth. So basically DNN is an extension, or you can say a more complex version of ANN, where you are having more data, more layers. If you go back and try to look into this, so you will see that this looks lot way similar, but if you will see this yellow section, this has been increased a lot. That means the hidden layer has been increased a lot so that it can deal with the more complex data. It can deal with the more high dimensional data. Okay, that's why we have kind of investigated, or we have started using the DNN. Okay. So now if you will try to look into the DNN, you can see this deeper architecture allows the network to learn hierarchical representation of the data from a very simple features, and DNN can often actually include a wide variety of specialized layers such as conventional layers, or the map pooling layers, dense layers. So there are several kind of layers, and each of these additional layers, they always add some kind of complexity in your model, but with that they also improve the model's ability to understand the data. So basically what you can see here, so the more you will be increasing this layers, so your model will definitely become complicated, right? But your model will have more capability to understand more complex data, right? And that is the reason, or that is how we kind of develop the DNN depending on our need, right? So now you will see that, as I said, that there can be lot of lot of layer. One, as I said, convolutional layer. They are very, very excellent when we talk about the image or spatial data, and they are also one of the layer which is being used a lot, which is being called as a dense layer. So dense layer is fully connected layer that can integrate some kind of features in your model as well. So the main key advantage of this kind of DNN over the ANN, I think you have already understood that the depth of the better representation. So basically more layers can actually help us or the network to extract and combine features at multiple levels of abstraction. They do also bring some kind of flexibility. That means with the right kind of architecture, if you can choose that, DNN can be adapted for, as I said, images, speech, text, tabular data. They are absolutely great for those. And then again, in many of the fields for autonomous driving to the healthcare diagnosis, they are really good forefront because of their unmatched predictive layer, right? So, or unmatched predictive power. So you can see that actually traditional ANN, they laid the foundation for neural network but are limited to simple tasks, and that's the reason there are a lot of this neural network has been developed, and DNN is one of those deep neural network. They build on this foundation or extension of ANN and adding more layers, more complexity to tackle the high dimensional data, to tackle the more noisy data, more uncertain data, and large scale data problems. So that's the reason DNN has actually been introduced in the market, right? And by enabling model to process input a layered hierarchical manner, deep learning actually allows us to address problems that were once thought too complicated. Like if you think about ANN, right? They may not be able to use with ANN. So again, this, as we say, that this is the simple diagram and the simple difference between the ANN and DNN, right? So ANN has only one or two hidden layer, right? Whereas which is suitable for simpler tasks, as we know. But when we move to DNN, and there are other kind of neural network also, we like CNN and those things. Like we may not cover all of those in the lectures, but that's how actually the neural network has been extended, for the demand of the different kind of tasks. So yeah, as we said that the DNN, as you can see, there are many hidden layers, right? For the complex problem, the more the layers will increase, the more complexity will increase. That can handle with more high dimensional data, more complex data, and that's the actually how generally these two kind of neural network looks like, right? So now, as we said, that deep learning has seen a very remarkable progression of architecture, each building on the strength of its own procedure. So here you can see the list of some of the key models. I think I have went till 2023 because I have followed a paper where they were talking about, and it's been published in 2023. But if you are interested, there are a lot of models have also been developed. Like many models have been developed after 2023 till 2025. So you can go and have a look into that. So you can say that we have actually started with 1998, right, which is a pioneered conventional neural network, which is CNN, that has been actually introduced all the way. And then there are some major milestones have also been introduced. Some with L-8, which has been started in the year of 2012, and they have been sparked the new deep learning revolution by dramatically outperforming the other methods on the ImageNet computation, right? And then there are many other ones which is kind of like GFNet or BGG, which came around 2013 to 2014, and they actually brought an architectural refinements with deeper networks and small conventional features, right? And then definitely around the 2015 there is an RDSNet that has been introduced for the residual connection, and that makes the trading very deep network or deep network feasible. And then following that, there are a lot of other ones like Yellow series in the year of 2016, and that has been actually used for the real-time object detection for a practical reality. So these are actually the diagram. You can see that how the popular architecture over the year has been changed, and and they actually highlight how deep learning architecture have been matured over the past 25-26 years, from early nets to till this year in 2025, right? And how it has been actually opened a lot of new facilities to use the deep learning in the architecture. And then when we talk about the deep learning architecture, we cannot simply ignore the CNN, right? So CNN is definitely a very, very important or a very kind of useful method, and is being called as a conventional neural network. CNN, as we know, is a type of multi-layer neural network that is being also inspired by the animal visual cortex, right? And they are very, very essential how our brains process visual information. And these biological inspiration actually makes CNN very particularly effective for image processing. They are very, very good at image processing application. We use this quite a lot there. So unlike traditional fully connected networks, the CNNs apply convolutions, like small features that can scatter over the input, right? Which allows them to efficiently capture the spatial and hierarchical patterns in data, such as like edges, or some kind of texture, shapes. They're very good in those kind of cases. So the first CNN has been created by the GIAN chain, and it's a pioneer engineer field of the deep learning. At the time, CNN used to be applied into the practical problems like handwritten character recognition. Like you can see like 5-6 writings, and you can see or that which character recognizations is it, like whose handwriting or something like that, or including the interpreting of the postal code. Those are the cases in the beginning CNN is to use a lot, and this early application actually demonstrates the CNN's strength of understanding, and it's categorizing the visual data, layering the groundwork for the very powerful model nowadays, the way we kind of use it, right? And CNNs, as we said, they are very deep networks, meaning they consist of multiple layers, right? And each layer serve a very specific purpose. So there are like a lot of early layers. The early layers automatically learn how to detect the low level features such as edges, corners, or simple textures. And then there are deeper layers, and that actually can combine these features like high level representation such as shapes or object parts. And finally, they do also have fully connected layers, or you can say, which has been also called as an output layers. They actually use this, these kind of layers actually learn the features and perform classification. They perform detection. They also perform some other kind of tasks. And if you will see that this kind of hierarchical feature learning is what actually helps the CNN to outperform the traditional methods like image classification or object detection. So those were the conventional methods, and how CNN is actually better than that. So now if you will look into the CNN's revolution throughout the period, you will see that CNNs actually revolutionized quite a lot in the computer vision, because they eliminate the need of manual feature extraction. Instead of requiring human or to define the image features, they actually learn them automatically from the data. And that's where actually CNN works really good. And this makes them not only more accurate, but also more adaptable when you think about different domains like medical image processing or autonomous driving, or even the image processing of the large scale data of composite, or the meta image processing. So those are the places actually CNN works really, really good. And as we said, that inspired by the human visual system, first CNN has been developed. They have performed quite a well throughout the years and developed and been used as a powerful tool for especially solving the complex image processing from the last so many years, right? And this is how generally it could possibly look like. Now, if you will think about another L-8 which is also being designed in the year of 1980s or the early 1990s. This is a very classical example of how conventional neural networks are structured. It was originally developed, as we said, for the written handwritten digit or recognize the postal codes. So basically, the strength of this L-8 architecture, they can be divided into mainly two parts. The first one is the feature extraction, and the second one is the classification, as you can see in this diagram. This can be divided into the two particular sections. Okay. And then also they do have like input layers, they do have conventional layers, as you say, they have pudding layers, so they do have several layers. Basically the input layer, if you can see here, the first one, they mainly is being divided into very small regions which is being called as a receptive fields, and this makes it easier for network to process the local patterns from the data, right? And as you say, they have conventional layers as well, they have pooling layer which is downsampling, and then once these layers are there, then there is a repeat convolution or the pooling layer is there. So basically you will see that they all are fully connected layers, right? And they are having a multi-layer perception. So the final output of the layer, which you can look into this one, the final output layer contains of the nodes which corresponding to each of the class. For example, digits 0 to 9 in handwritten digits or recognition, right? So the network actually uses a back propagation method to learn and adjust the weights during the training period, and that's how it generally works. So now if you will see this kind of methods, they were actually very revolutionary because it introduced the now standard concept of layered feature extraction, which is now being used a lot, pooling to reduce the dimensionality, as well as end-to-end training with the back propagation. So these were the three important the standard concepts. That's been the reason they were being used a lot. And if you will see by simply in today's standards, you can see that this kind of methods, they paved way more modern in CNNs like LXNet or BDGNet or somewhere like RDNet. So those are the cases it actually kind of, ResNet, it actually uses bit quite a lot. So these are actually demonstrated that how the CNN could automatically extract and learn the features from the images and then classify them with higher accuracy. So now when we talk about this CNN evolved from the L-8 to more sophisticated model, and now if you will try to look into the real life applications, especially if you think about the civil engineering application. So another very good application is the detection of the concrete cracks using the CNN. Okay. So as we said that this has been developed like Chai et al. I think I have also given the reference of all of these papers, so you can go back and have a look into these papers as well. So you can see that the Chai et al. They have developed a new CNN architecture specifically designed for crack propagation or specifically designed for crack detection in the concrete structure. And this is a prime example of how deep learning actually or originally built for image processing tasks like, as we said, the handwritten character notes and those kind of cases. So in this case, we are considering about the structural health monitoring or infrastructure monitoring. So if you will try to look into this particular images here, so what happened is that first you input the image, right? That means the process begins with input the image of concrete surfaces, and this image contains pattern of cracks or intact areas that network needs to classify. And then happens the work of the conventional layers. The network uses, there are several layers, like they can have, you can see that they have like C1, C2, so they use their conventional several layers to extract the increasingly complex feature from the image, right? And each layer applies small filters to capture local images, like they can capture the age, they can capture the crack pattern. So that's where each of the layer actually works. And once that is being done, then what is the next step? Is the batch normalization and pooling. So basically batch normalization layer has been then used to help to stabilize and speed up the training. And once that is being done, then pooling layers start working. So you can see that it's been noted as P1, P2. So that's where the pooling layer works. And what pooling layer does is that they kind of perform the downsampling, basically. Basically reduce the dimensionality of the data while reading the most important feature in the data, right? This is also very lower computational cost and prevents overfitting. So that's another, the advantage of this kind of model is. So and that's how it works. And then now what is the next step? The next step is that the dropout layer, right? So what dropout layer is done and why it has been introduced? It has been introduced between the layer to randomly deactivate some of the neurons during the training. Okay. And this technique actually helps you to reduce the overfitting, and they also improve the generalized to unseen data. That's where it has been introduced. So you will see that there are a lot of layers, and all of those layers have some kind of specific work to do, and for each of the cases we kind of use it in each way. Some of the layers will not be needed if you kind of think about other kind of monitoring. So once the dropout you can see it's been mentioned here. So once the dropout layers are being done, then the next one is the fully connected layer. Okay. So after feature extraction is being done, after downsampling is being done, so the flattened features are fed into the fully extracted layer, and that's been called, as you can see, that L6, L7 and L8. Okay. They are very similar to the traditional neural network which we see in nowadays. And these layers actually combine the all learned features to form a final decision, right? And then what is the final layer? And that is the out layer. So output layer. So what output layer does is that the network produces two main outlying columns. One is the crack. So if the image contains a crack, and another is the intact. That means the image does not contain any kind of crack, right? So you can understand that how it actually, the whole all of this layer, how it actually works out. And here we are talking about the CNN for the case of concrete crack. So first we are inputting the image, then we are using the conventional layer like C1, C2, right? And then we are doing the back normalization and we are doing the pooling. Once that is being done, we go to the dropout layer. Once that to kind of take care of the training the data to avoid any kind of overfitting. And once that is being done, we kind of fully connected layer to get all the data into one place, right? And that is being said as an L6, L7, L8. That we kind of create all the fully connected layers. And once that is being done, we kind of go to the output layer. And output layer will give you like two types of image, whether there is some crack or there is no crack. And that's how it generally works, right? So as we said that, so if you will see this kind of model, so basically that's how it works. They do have different kind of layers have different work to do. Depending on your application, you kind of, do the work accordingly. And similar way, you kind of use the other neural network also. You will see some way the behavior or the work at least is some way similar. So you can see this kind of, this particular method or, the GIAN CNNs for the crack detection, they take images as we say, with the help of multiple layers of the feature extraction, they kind or pooling, as we said, or fully connected layer output, they kind of let you know whether your surface has some kind of crack or you don't have the crack, right? And this approach demonstrates the power of and flexibility of the CNN to move beyond the traditional application, right, into very new field of civil engineering. And that's how we kind of use the CNN. And then there are definitely other ways of doing that. There are a lot of other research has been done in the area. If you are interested, you can have a look into the other kind of application as well. Okay. And now, when we talk about the conventional neural network for spatial data, now there is another powerful deep learning architecture, specifically when we talk for sequential data or when we talk about the temporal data. And that method is being called as an recurrent neural network, and that's also being called as an RNN, right? So this kind of network are highly effective for modeling sequential data such as sound, speech or text, right? So unlike the conventional neural network, which are great at interpreting the static or non-sequential data like images, what RNN are good at, so RNN excels at capturing patterns over the period of time. For instance, a series of words in a sentence or frames in a video, so they are very, very good in capturing those. RNNs are also being quite useful for spatio-temporal features like features that evolve over the time, features that evolve over the space. And they can also even be combined with CNNs, and like RNN and CNN can be combined together to solve a very complex computer models or very complex computer tasks like such as action recognition in the video or those kind of things. So now if you will try to look into this RNN, the RNN actually processes data step by step, and they keep the tracks of previous inputs using the internal state of memory. So this memory allows the network to understand the context of the current input situation, which is based on the input that came before it. Okay, so they need to understand that, and how. So here's how it differs from the traditional feed-forward neural network. So basically, in a feed-forward network, what happens that each input is treated very, very independently, right? And the model only looks into the fixed context window. Whereas if you look into the recurrent neural network, or if you look into the RNN, what happens, this model considers all the kind of previous input you get when making a prediction, right? And that actually creates a much richer understanding of the sequences. So the ability actually helps, or this ability actually makes the RNN especially very, very powerful when we talk about the predictive model, because it takes care of the history. For example, prediction of the next word in a sentence, right? When you kind of write an email, you will see that sometimes you always get a prediction of the what word could possibly come, right? So those kind of things can actually be very, very good when you kind of try to use the RNN. And training the RNN typically involves, there are some method called backpropagation through time, which is also called as an BPTT. So we can use the BPTT and some real-time recurrent learning method to train these things, which account for the dependencies between the time system. And this method actually allows the RNN to adjust the weights not only based on the current input but also the previous incidents or the sequence of past inputs, and that's how it actually helps to train the RNN. As we said that it has a varieties of the long list of applications. One is the NLP, if you have heard about the natural language processing. So basically machine translation, sentimental analysis, or text generation. Those are the places RNN being used quite a lot. Then speech recognition is also something where you are converting your spoken words into a text or identifying the speaker's characteristics. That's the place also where RNN being used a lot. And then time series forecasting, video analysis. So there are a lot of applications where RNN can be used a lot. So you will see that this kind of network are designed to remember and utilize the past information to make a better prediction about the current and the future situation or the current or the future input. And their ability to model the sequences that actually help them to make a natural choice for problem involving the time dependent or the order dependent data. So as we said that we explored the fundamental of RNN, then we can also have a quick look into the visual comparison between the feed-forward network, which is the A, and RNN, that how it's actually could possibly look like, right? Because it has also a little bit of similarity. So the feed-forward network, which is also been called as an FFN, yes. So in a traditional deep learning or the feed-forward network, what happens? Input and outputs are treated very, very independently, right? So the information flows in one direction from input to the hidden layer, then to output, right? With no memory of past incident or past input. And this is great for like static tasks like image recognition, but not ideal for sequencing. Whereas if you look into the RNN, so by RNN actually introduce loops in the architecture. We will compare with the feed-forward network to the RNN. So the output at each step that depends not just on the current input, they also depend on the previous input which has been stored in the network state, right? So this allows the RNN to model the sequential data, making them effective for tasks and all of this. So that's where the difference comes from the feed-forward network and RNN, right? And definitely there are some kind of challenges and limitations of RNN. RNN excels at sequential modeling, but they suffer from issues like vanishing and exploiting gradients during training, or that can actually limit how for back in sequence RNN can remember. So because we are using RNN because of the fact that it can remember the previous details, but some cases it can vanish and explode those gradients, and that could be another problem, right? And then to address this kind of limitations, there are definitely some kind of advanced technique has been developed, which is one is being called as a long short-term memory, which is being called as LSTM. Is being used quite a lot, which has been proposed to handle the vanishing gradient problem, right? LSTM introduces the memory cells. They also introduce the gates that control the flow of the information, and they also allow the network to retrain the information over a much longer sequences. And then there are another kind of gated recurrent neural network also that also kind of help these models to refine the reduced data, refine the the reduced training error, and improve the performance by getting information flow, right? And then there is another one which has been called as an ReNet. So this is also actually combine the RNN and also combine the CNN, and for the task like image segmentation. Those are the places we try to use this ReNet. And this is actually a very hybrid machine learning model or hybrid machine learning approach that exploits the CNN's spatial feature extraction and that uses RNN's sequential modeling. So these are the two things, and that actually giving them a very powerful extraction for computer vision, right? So if you will try to look into this RNN, as we said that they are evolution from simply forward network to more sophisticated RNN. And their extensions are really, really good. So they are very good at they do not work like a black box definitely. And they have a lot of kind of advantages compared to the conventional neural networks, right? And then when we talk about the deep neural network, there is another important one which is being called as an FCN, okay? So, if you will now move from the feed forward to the recent network to another powerful deep learning network, which is being called as a fully conventional network, right? And that we in short we call as an FCNS. And this model is especially important in systematic or semantic segmentation, where the goal is not just to classify an image, but to classify each pixel in that image. And that's the period when we use FCNs, right? So FCN was being developed by Long et al. And they represent a major step forward in computer vision tasks. Instead of using CNN only for classification, you can use the FCNs to modify time to perform the pixel-wise classification and assigning a label to every pixel of the input images, right? So now if you will see the FCNs are built on the top of well-known architectures such as GoogleNet or AlexNet or BCG16. So the key innovation is to replace the fully connected layers with the convolutional layers, enabling the network to maintain the spatial information or the spatial details, right? So definitely there is no fully connected layers. So by removing the fully connected layers, what FCN does is that FCN reduces the number of learnable parameters dramatically, and this makes the network very fast. This makes them very computationally efficient, which also preserve the ability to process input for varying sizes, right? To achieve the pixel dense output, the Long et al. Also introduced another details, which is an unsampled stride convolution, and that's been called also as a transport convolution. Okay, and this states actually reverse the downsampling from earlier layers, and that actually help you to get the original input size for segmentation, right? So there are a lot of advantages of FCN. Definitely, there are a lot of applications as well. The main advantage, as we said, the speed and efficiency. Because without fully connected layer, FCNs can process the input more efficiently compared to the CNNs and other neural networks. And then the another one is that dense prediction. So that's another thing, that instead of producing a single class level for the whole image, FCN actually produces a map of classification per pixel, right? That is very essential for the tasks like object boundary detection or medical images. So those are the places we do use it. And then another advantages of this FCN is actually end-to-end training. So basically, the entire model can be trained end-to-end for the segmentation, unlike earlier patch-based methods or those kind of things. So as we say that they do have a lot of applications like medical image analysis. So you can, like for tumor and the some lesion detection, you can use that. For civil engineering craft and defect detection for the infrastructure, we do use it. For environmental monitoring, we can use it for land cover classification in the satellite imaging, those kind of things. So you can see this FNN actually marks a shift from the image level classification to pixel level understanding. And by estimating these fully connected layers and adding the more deconvolution for upsampling, the FCNs have made a very semantic segmentation for fast, accurate and practical for real world application, right? And now here you can see that this is an application of deep neural network in the image and the sensor data analysis, especially when we are talking about the SHM cases, right? So here you can see that how deep learning can be integrated with different kind of sensing techniques to detect and classify the damage in structures, ensuring the safety as well as the reliability, right? So at the top you can see that we see two types of methods. One is the local method and one is the global. So what do we mean by local and global in SHM?
Local means at a particular location, like if you talk about the buildings, if you go for any particular beams or any particular column, that is called locally. But when you talk about in the complete system, then it is called about the global.
Yeah, correct, right? Are you all agreeing with him? And so then that's how we try to develop it. We try to talk about the whole structure of that, and then we are also trying to differentiate between the local one. That means a very specific region, that how this deep learning method can actually be used, right? So for the local, as I said, that local always focusing on the specific region or the components of the structure, and global provide a holistic or the system-wide assessment for the whole structural health, right? So deep learning methods can actually be divided into imaging, they can be divided into the computer vision, and they can be divided into the vibration-based method, right? So according to this kind of different approach, I have tried to kind of divide it according to the sensor, and then what are the methods you can possibly use into that, and then what are the information you could possibly get. Okay, so I think this is a very good, I will say a good representation. And if you will try to look into this diagram, you can see that how deep learning can actually transform the SHM from the traditional manual inspection to the automated high precision and predictive systems by combining the local image methods to the global vibration based analysis, right, and computer vision with digital twin technology. So we can actually achieve the real-time monitoring, early damage detection, and better maintenance planning for critical infrastructure. This is a very good, I will say the good figure to kind of have a look into that and try to understand that how this could be used in the throughout the process. Then again, we will kind of try to look into some more practical and impactful application of deep learning in structural health monitoring. So one of those is that damage classification. So when we talk about the SHM, damage classification, they means using the deep learning models to automatically categorize the image as either damaged, right, or healthy or intact, right, or to classify some specific types of damage. So this is to major advancement compared to the traditional manual inspection method where it allows the much faster, scalable, and it's very reliable. Also, when we talk about the structural monitoring and how it actually works, so the process actually involves training the deep learning model, right, on thousands of level images. You take a lot of images using satellite, using drone, and then you input the images and try to train the 1000 level, whatever, I mean, it could be 1 lakh also, depending on how many you take, kind of train the model, right. The model then learns to detect and classify various forms of structural damage from new and unseen data, right. So the input damage is analyzed by the model, and the model then outputs a category, as example crack, mold, some kind of joint failure, tile deterioration, something like that, right. And the entire input image is thus grouped into a specific category as a final output, correct. So now if you will try to look into this table, you can see that I have tried to summarize some of the key studies and activities in the deep learning, especially based on the damage classification. So there are CNN models like those like GIAN, which I said, they kind of try to identify the cracks in the building with high accuracy. And there are a lot of other studies like AlexNet, DSN, and then meta-learning CNN. So meta-learning CNN have been used to classify the cracks in the buildings, bridges, and pavements. So this table is also lists the training, validation, and testing data size as well. So if you are interested, you can try to kind of look into that and try to understand that what is the different way to use this kind of different deep learning models for different cases. And basically you will see the main advantages they are looking into. There are like 4, 5, 1. First is the automation. So basically they want to reduce the manual inspection, they want to reduce the human error. Then they want to speed up the process, and that means process a large amount of data very rapidly. And then they want the accuracy. That's another important factor they are interested about. That means high precision and the accuracy rate ensure the trustworthy result, right? And then the versatility. That means that it can classify the wide range of damage type. It can be crack, it can be mold, it can be fatigue, joint failure, some kind of deterioration. So it should be trained such a way that it will not be able to only catch or detect one type of damage or data. It should be able to type multiple type of those things, right? So basically you will see that they have studied this deep learning based damage classification that actually represents a transformative approach for structural health monitoring. By leveraging this kind of powerful techniques what they have talked about, the CNN, AlexNet, DDG, meta-learning CNN, we can actually very quickly and accurately classify the structural defects at a different length scales, making the infrastructure more maintenance safer, more efficient, as well as more effective, right? And then if you will try to look into how CNNs actually outperform the traditional age detection method for crack detection. So let's try to kind of compare the CNN versus the traditional method, okay? So historically we know that the crack detection relied on age detection algorithms such as Sobel or the Canny filter. You must have heard about it. So basically there are several traditional methods or the human the methods. There is a several way that you kind of try to understand the crack or the damage or those kind of things. So age detection algorithm or the Sobel or the Canny filter are those algorithms which are generally being used historically and they are being relied historically. So they are very effective to certain degrees because these traditional methods struggle under the real world condition like poor lighting or if you have shadows or blurriness or surface noise, so then these algorithms are not good, okay. So whereas if you look into the CNN based approach on they kind of learn directly from the data, right, and they extract the complex features automatically. So as a result CNN shows a very superior performance, right, even under the challenging conditions where traditional methods can fail, right, like the methods like as I said age detection algorithm or Canny filters, those kind of methods, right. So now if you will see the diagram here, that how CNN actually kind of work, or CNN based damage detection actually work. So as we said, first we input the image, right? That means we start with an image of surface which contains some kind of potential crack, some kind of damage, right? So once we input the image, the next one is that sliding the window technique. That means the image is divided into small kind of patches, right? Using a sliding window. Each patch is analyzed individually, ensuring no part of the image is missed. Correct? And once that is being done, then the training of the CNN classifier starts. That means that these patches are then passed through a very trained CNN model which has learned to differentiate between the crack and intact. That means you have a structure, you divide it with the patch wise, and you should be very, very careful that no part is being missing, and then you put it into the CNN model. CNN model is already been trained what is crack image look like and how the crack image will look like. If there is any other issues, then how should it look like that, and then it will pass through that CNN phase, right? So once that is being passed, then the next step is output image, right? So that is going to tell you that by combining all of this, the final output, that whether there is any damage region, there is a locally marked one. So that's how generally it works out. So there are a lot of benefits for this, as we said: high accuracy, automated feature learning, there is scalability, there are robust localization. So these are the ways generally we kind of try to do the CNN for any kind of damage classification, right? Is it clear the whole process to everybody? So now let's try to look into the another case, which is the pixel level damage segmentation, right? And how actually it works. So traditional methods, as we said, they are usually detect the damage using the approximate bounding boxes, right? Which can only give a rough estimate of where a defect is located. So in contrast, that pixel level damage segmentation with deep learning, they kind of help us, so they kind of allow us to identify the defects pixel by pixel. And that makes it much more precious, right? So this method can accurately outline the shape. They can also help us to understand the size, the location of the defect, which is essential for understanding the full text, right? So it's not only saying that the damage and the healthy, it is actually telling you the size of the damage, the location of the damage, the intensity of the damage, or the shape of the crack. Everything you will be understanding. And why it is important? So by pinpointing the individual damage pixels, this approach gives us a much clearer picture of defect geometry, as they said. This is especially useful when the small cracks or corrosion patterns may otherwise go unnoticed, right? When you can't see with your naked eyes, or you cannot actually understand that there are very, very small cracks, that's the time or the period when we kind of try to use that. It also helps to quantify the damage more reliably, as we said. It helps us to make a more data-driven maintenance decision. So how it actually works, similar way we'll try to look into how it does work. So most of the deep learning models for segmentation, they use the encoder-decoder architecture, right? So what happens is, first we use the encoder. That means the encoder extracts the feature from the input image. So if you give the image, so encoder extracts some kind of feature from the image. They capture the critical information about the potential damage, and then what we do? Yes, decode it. Yes, right. So the decode restores the original spatial dimension of the image while marking each pixel as damaged and intact, as you can see in this figure, right? Okay. So basically the input image of the damage structure goes into the trained deep encoder model, and then the output image, if you look into this one, they kind of highlights every damaged pixel individually. Essentially, they kind of try to create a very high resolution map of defects, right? Again, the benefit, the similar way, they do also have a same benefit: high precision, quantification, automation. So those are the three main benefits that the defect, they can tell you the shape, age. They will also help you to understand the damage area, the length, the width, and they reduce the manual inspection also. They save the time, they save the cost. So those are the main benefits of this kind of models. So in summary, you can see that this kind of pixel damage segmentation, they take the deep learning beyond just spotting the damage compared to the previous one, right? It allows us to a highly detailed pixel-wise analysis. So now let's try to look into the boundary box level damage detection. That is also another important application when we think about structural health monitoring, right? So methods like, we use traditional method like sliding the window technique that have fixed the sizes, and often sometimes means the damage that does not fit neatly into their personalized region, right? And maybe even you can think about that. You may kind of divide it into small images, and you may have some sizes of those small windows. Sometimes it could possibly happen. Some of the age may not fix into that window because all windows have some similar size, and that process is called as a sliding window technique. And you may miss some of the parts, right? And that's the time when we try to use some other kind of method, because this is the limitation that can make it difficult to accurately detect the damage or localize the damage. And that's the time when we use some kind of deep learning methods, and which offers us much more flexible and effective solution. So how does actually it work out? So if you think about with bounding the box level detection, right? If you take a very trained deep learning models, for example, you take a faster RCNN, okay, which identifies the area of the interest in an image and draws the bounding boxes around the potentially where the damage actually exists. We will now look into the figure. Let's start looking into the figure and try to understand. First, we start with the input image of a damaged surface, right? And then the image is passed to this trained object detector, which extracts the key features and predicts where the damage is located, right? And then what we do, then we get the output image. It displays the multiple bounding boxes, you can see here, which is been actually kind of given with the multiple bounding boxes here, which is overlaid on the crack or damaged region, localizing them very, very precisely, right? This approach automatically adapts to vary the sizes and shapes of damage rather than being limited to fixed windows compared to this one, right? Did you understand the difference between this one and the previous one? And then advantages, again, they have a lot of advantages. There is a flexible detection, that means it can detect the damage of different scales, different orientation, different sizes very, very easily. They are improved with the localization. Their speed and efficiency is also very, very good. Their scalability is also very, very good. So basically the bounding box level damage detection, they kind of bridges the gap between the simple image classification and detailed pixel-wise segmentation, right? So it actually combines the speed, it combines the flexibility of modern deep learning algorithm architecture with the precision which is being required for practical structural health monitoring or practical infrastructure monitoring, right? And now let's try to look into the basics of reinforcement learning and try to understand how it works for the simple world analogy, right? So what do we mean by the reinforcement learning? We have already seen. It's the type of machine learning where the agent learns to make decisions by interacting with the environment. You remember we have seen it yesterday, right? It receives the feedback in forms of rewards. It receives the feedback in terms of penalties, and then it goes back, it adjusts its behavior and it improves the performance, right? And the ultimate goal of this agent is to maximize the cumulative reward over the period of the time, and which is often called the return, because of this dynamic RL is particularly suited for sequential decision making problem, right? And now if we will try to understand in the real world analogy how this concept actually works. To make this concept very easy, try to imagine a child learning to ride a bike. The child represents the agent here, right? And the bike and the surroundings, they represent as an environment, right? So if the child pedals correctly and maintains the balance, they move forward very, very smoothly, and this is the positive reward, right? And if the child falls, it's a negative reward, but it's also a learning moment, right? If the child falls, it's a negative reward, but still it's a learning moment. That means over the time, the child refines their action, learn from the environment, and also called as a policies, achieve the goal of riding the bike more effortless, right? And this is exactly how the reinforcement learning also works, right? They learn from the environment, they learn from the trial and error, they go back and they kind of try to behave or try to get a better performance, right? So then, as I said, that the reinforcement learning, they essentially mimics how humans could learn new skills by experimenting, by receiving their feedback, by improving their performance, okay? So in AI systems, you can see that this algorithm also acts as a brain of the agent. Because it enables us to make you smarter decision over the time. Okay. So basically, this reinforcement learning is very, very powerful because it can solve complex problems where the correct action is not obvious, right? But it can be learned through the exercise. It can be learned through the environment, it can be learned throughout the reward, it can learn throughout the penalty, right? Just as the child gradually becomes skilled at a cycling, RL agent can also, and it does actually improve his decision making as and very interact with the environment, right? Now let's try to see some of the key components of RL. The first one is agent. So what did you see what is agent yesterday? Who is the agent? Sorry? Environment is not the agent. Agent is learning from the environment, right? Agent is the decision maker or the learner, right? Who is learning for this. So basically that's what the agent job is. It interacts with the environment, it makes the choices, it learns from the feedback and it receives the feedback. So basically the agent's ultimate goal is to maximize its rewards over the period of the time. Isn't it? And then what is environment? Yes, external surroundings, right? From where the agent is learning, when the agent is reacting, it provides feedback, right? New states based on the agent's action. Example, if you think about in a maze scenario, the maze itself, with its paths and walls, it's an environment. Now, what is the state? State is a snapshot of the environment, right, at a given point of time, and it contains like all the information the agent needs to know or needs to learn to make certain decisions. And then the another one is the action, right? So actions are also possible choices of availability to the agent at any given point of time. And then reward, we know that the rewards are scalar values like received by taking an action. So they can provide agent desirable behavior by providing positive, or it can be negative, right? Both can be possible. And then the policy is actually the strategy, or policy is the mapping from the state of the action, right? It defines how the agent could behave at any given point of time or at any given point of state, and that's been called as an policy. And then there are two other ones, which is the value function and another one is the Q value. The value function actually estimate the expected long-term reward for a given state, right? Considering the policy being followed. And it helps the agent to evaluate the desirability of the states. Whereas Q value, it goes a step further from the value function and it represents the expected reward for taking a specific decision or for taking a specific action or at a specific state, okay, under the current policy which is being taken. This helps the agent to choose the best possible action, or this actually helps the agent to take the best as possible path to get the maximum reward. And that's the what T value does. It also been called as an actual value function, right? So you will see that these are the main 8 components of the RL, and together these 8 components form the foundation of any reinforcement learning system. So the agent interacts with the environment, right? It evaluates its state and selects the action, defines the policy over the period of the time based on the reward it receives. So understanding these building blocks make us very, very easy to design and implement the RL over the period of time, very, very effectively, right? So now let's try to look into the another one, which is the Q learning. Okay, so Q learning is also a very value-based one and of policy reinforcement. So this is the continuation of the Q value. So we are seeing Q value. So the next important one is the Q learning, or the last one. Okay. So what is Q learning? That, as we said, that's a value-based of policy reinforcement learning algorithm. This means that it learns the value of taking certain action in a given state, right? Even while following a very different policy for exploration. So it means that the purpose is to find the optimal action selection policy for a given environment for the agent. Okay. So that's the final or the very advanced process of the reinforcement learning, or the last step of the reinforcement. So the Q in the Q learning refers to the quality of action taken in the particular state. Okay. So the algorithm builds a Q value function which represents the expected future reward of taking an action A in the case, right? So now if you will try to quickly look into this particular diagram here, you can see that how agent is interacting with the environment, right? The environment provides the state S, the agent chooses an action A, right, based on its current policy, and then it receives a reward which is being called as an R, and it moves to a new state, right? Then the learning algorithm updates the Q table. That means they look up the table which each of the cells stores the value of a certain action in a certain case, right? And using this Q table again, this one, the agent will again learn from the trial and error to how to make the best decision over the period of time without needing a model to the environment, right? And this is actually the whole component of the RL and how it actually works. Clear to everybody? And now here is that step-by-step working of the Q learning algorithm, or which is the key components of RL. So again, the similar way that let's try step-by-step to understand this. First is the initialization, right? So what we do, we start by initializing the Q table. This table holds Q values. We estimated the expected reward of taking a specific action or a specific state, right? Initially, all the Q values are set to 0. And then we also pick the initial state. So that's the initialization. That is the step 1. So what is the next step? Choosing an action. That means the agent selects an action to execute from the current state, right? This selection is often made using a E-greedy or the IPSAL and greedy policy, and which balances the exploration. That means trying some kind of new actions, right? And exploration, and that knows and that will give you, the agent may know that can give you some good reward. So you, after the initialization, you choose some kind of action. So what is the third step? You have to observe the environment first. You choose an action, and then you have to also observe the environment, right? You first have a Q table, which is this one, and everything is set to 0, okay? And once you see the Q table, then you choose an action. The action to execute from the current state. And then you need to learn from the, or observe the environment, right? Once the action is being taken, the agent, then you have to receive some kind of feedback from environment, isn't it? So once you select some action, you will be receiving some kind of feedback from the environment, and then you will go to the next stage, isn't it? So how the whole process is being done? First is what step? What we do?
Environment you have already, there is several states, and the agent choose any one of the action.
Yeah. They use any of the action, and after that what happens? Yeah. So after that what happens? You choose an action, right? So whether your action is going towards the correct or not, you get some feedback. And from where do you get the feedback? Right? So basically, once you choose the action, then the next one is getting the feedback from the environment, right? So that's basically your third step, that observing the environment, right? That means that once the action is taken, the agent receives some kind of feedback from the environment, and that can be included as a reward. That been said as an R. So reward can be positive, reward can be negative, depending on the action, doesn't matter. And then what is then is the next step, right? Which is so we generally call as an H dash, H1, whatever you want to say. We have said as here, whatever you want to say, right? So now once the step gives the agent valuable information about the effect of its action. So what is the next stage? You have a key value, right? Then you have taken action, get the feedback. So what you do next? Yeah. Yeah, you update the Q table from the feedback you got it, right? So the agent then updates the Q table for the state of action, like Q learning updating rule. There are a lot of ways you could possibly do that, right? And then once that is being done, then what is the next step? The whole learning cycle will go like that, correct? That's how generally RL works, right? Clear to everybody? And now here you can see that how an agent interacts with his environment. As we said, first is that agent observes, right? This process begins with the agent in a given state. So you start observing the environment. This is where it gathers all kind of information. It needs to decide the next one. And then is the agent acts. How does it actually act? What it does, it based on the current knowledge or the current policy, the agent select an action from the Q table, right? And then we said the environment reacts, correct? And then the agent learns, and similar way, observe, act, react, learn. So these are the 4 activities which keep going on. Correct? And now if you will try to explain the mathematical foundation of the reinforcement learning, and that we generally use it using the MD process, which is the Markov decision process, right? Which is also been called as an MDP. So almost all RL problems they can model as an MDP because it provides a structured way to represent the decision making over the time, right? And now if you will try to kind of look into this equation here, so basically if you will try to look into this MDP equation where the S represents the all state of problem state, basically every situation the agent can find itself in, right? And the A represents the all possible action the agent can take from any state. Whereas P represents the transition probability function, gives us the probability of moving to the next state after taking an action of the state S, right? And R is the reward function, which assigns an immediate reward for taking any certain action. It can be positive, negative, depending on the situation, right? And what is here gamma? Gamma is the discount factor. Yes, correct. It tells how much weight to place on the future reward compared to the immediate action. Correct, right? So basically the agent's ultimate goal here is to show that the sum of this immediate and the future rewards discounted over the time. So in short, we can see that what this MDP or Markov decision process does, this provides you a mathematical framework that makes the reinforcement learning possible, right? That guides the agent to learn from the optimal policies for complex decision making state, right? And now, as we said, there are mainly 3 types of reinforcement learning algorithm with its own approach to the agent learn. First one is the value-based method. So this method focuses on learning a value function. For example, through learning, instead of learning the policy directly, the agent learns how valuable each of the state action pair is, or from the value of function, the policy or the agent decision-making rule is implicitly derived, something like that. And then another one is the policy-based method. So in the policy-based method, what happens is that the agent directly optimizes the policy without relying on any value function. Okay, that means it tries to improve the decision-making strategy directly, which can be more effective in certain kind of environment. Like a classic example can be reinforced algorithm. Okay, and then the last one is that actor-critic method. So what actually this approach is? This approach combines the strength of the both value-based as well as the policy-based method. Right? It uses an actor to propose an action which can be policy based and a critic to evaluate them that can be value based, right? And this combination offers stability, efficiency, faster learning, and this is another very good example of this kind of actor critic method can be the advantageous actor critic of A2C algorithm. A2C algorithm is one of the very good example of actor critic method. So basically these are the 3 categories that represent different philosophies how the agent could learn from the optimal behavior, either from values of states, either directly optimizing the policies or using any kind of hybrid of the both. So basically there are 3 types the agent could learn from the algorithm or from the environment and they could react accordingly. Okay. Now there is another, if we will try to look into another case study of the autonomous HVAC controlling using the reinforcement learning, specifically an advanced deep learning or deep Q network, which is also being called as the GIAN. So reinforcement learning, as you know, that trains an algorithm to make decisions by interacting with the environment, right? It receives rewards, it receives some kind of penalty, and this approach allows the system to learn optimal strategies over the period of the time, and that makes it well suited for complex dynamic cases like HVAC optimization, right? So here if you will try to look into this particular thing here, DQN, or we call it as deep Q network, that has adapted to optimize the HVAC system. And unlike the traditional HVAC controller, this kind of method, they simply try to minimize the energy consumption. What this DQN does is that this system focuses on reducing the energy cost. They're taking into the account of fluctuating the the electricity prices, and they also demand some kind of charges. So demand charges are fees based on the highest peak power consumption during a billing cycle or something like that. So basically you will see that using this kind of DQN or this kind of methods, it actually highlights that how these methods are being revolutionized over the infrastructure monitoring, and they can control by making the autonomous, adaptive and cost effective method. Okay. And now if you will try to continue understanding this kind of HVAC control case study, they do also talk about some kind of challenges, they do also talk about some kind of limitations by using the DRL, and DRL is nothing but deep reinforcement learning, okay. So as we said, the simulation result can show a very promising outcome, right? For instance, if you think about the energy cost saving of up to 6%, right? When including demand charges or 8% without them. So while these results are impressive, they are still significantly challenging to address before DRL-based HVAC, okay? So the system can be fully deployed in the real world. Before that, there can be certain kind of challenges. The first one can be for this DRL or the deep reinforcement learning is that they generally require a large amount of data to train. You cannot deal with the short data, you need to have large amount of data, and that actually highlights one of the RL's well-known issue, that is the sample inefficiency. That's one of the biggest issue for this one. And the process of collecting and processing the such large data sets can be costly, right? They can be time consuming, especially as well when you think about the real world environment. Moreover, retaining these models when conditions can change, they can become more difficult and expensive. Okay. So basically, one of the important or the limitations of this kind of cases is that the sample inefficiency. Okay. Second limitation of this DRL or the deep learning, deep reinforcement learning is that they often act as a black box in a similar way. That means that the decision making processes are not easily explainable. Basically, for facility engineers, this lack of transparency, that they can make it hard to understand by suddenly the system recommends some certain kind of control system or some kind of control actions, because you may not know what is happening between the layers. That means you give the input, you get your output, but what is happening in between that, you may not be able to understand that, right? And these are the kind of limitations, or these are the kind of challenges. They are very urgent to take care of that. And then there are definitely some certain kind of the methods which are being used to take care of this kind of disadvantages. So one of those are like more data efficient training method that is being used to reduce the amount of training data required without specifying the accuracy, and then improve the interpretability techniques. So they kind of help us to understand the reasoning behind the AI decision, so that it does not work as a black box. So you actually know that why you are getting some certain information, or why you are kind of getting this kind of behavior. So except the understanding the input and output, you can also understand that why this is behaving in a certain way, right? So that's another important thing, that improve the interpretability techniques. That's another important thing that we try to understand. So basically, if you will try to sum up this, you can see that DRL offers a powerful and innovative approach for optimizing this kind of systems, which actually help us the data efficiency and interpretability. If you will take care of those things, they can be really good if you kind of think about taking care of their limitations, right? Is it clear to everybody till now? Any further questions?
Yeah, on the slide number 44.
Yes.
Initially, we have in terms of image. What the conditional do, it will be just dropping some window sliding from there. And after the cooling, the size will be reduced depending upon how the cooling size.
Yeah.
Again convolution, again cooling. So at the last, we get the only very small size of the image rather than the original image. And if we apply the dropout on the smaller section, then there is a chances of losing the information, because we have already do some several type of cooling and several type of convolution. So my question is, how much dropout should be decided on the what basis the dropout should be decided? How much will be
Basically, why we use dropout layers? Because we want to take care of the overfitting. That's the reason we use the dropout, right? That actually depends on the problem, that how much data you are having and what could be the size of the output image you are getting. But generally, the dropout layer we basically use to randomly deactivate the neurons during the training, and it actually helps us to take care of the overfitting, right? It actually helps us or improve some kind of unseen data. But it depends on the kind of size of data you are getting, like the size of image you are getting and the output one. But generally, we need to use it because to take care of the overfitting. Yeah. So now let's try to do one or two of the quizzes, right? Let's see this one. Which models are most suited for the sequential sensor data in infrastructure monitoring? RNN, LSTM, right? How about this one? Which deep learning architecture is especially effective for image-based crack detection? CNN? So now, if you will try to look into the summary of what we have seen today, we have seen the classification model, we have seen regression time series model, we have also seen some of the decision tree, random forest, and other deep learning methods like CNNs, L-8, and some kind of FCNs as well. With that, we have also seen the damage classification by using the CNN, how we can actually use the damage classification. With that, we have also tried to see some reinforcement learning basics to understand that how could it possibly work by using MDP, Q learning, and those things. Then we have also tried to look into the types of RL algorithms, that the Q learning or the actor critic, and that also ended up that way. We have seen some kind of a case study for the DRL where we have seen some kind of challenges and future needs, right? So with this, I will say that we will end up this lectures, and where I will say to kind of think about the physics information learning to combine the structural mechanics with AI models, right? And then also try to understand the transfer learning and domain adaptation to apply the pre-trained models to the infrastructure, okay? So before we end the class, as we said that these are all the reviews which we have, or all the papers which we have followed in the lecture. So if you are interested, please go through one of these or try to understand. This is definitely not the tabular one. The tabular one are not being included here. That is itself in the tabular once you can refer it from there. So before ending it here, so I also want to quickly show you tomorrow's tutorial so that you can be little bit prepared with that. Yeah, so tomorrow what we will try to do or start in the tutorial is that we will try to build a deep neural network, okay, and by using the PyTorch. So this, what we will do is that we will import the library and setting up. From there, we will try to implement the CNN based work by using the PyTorch, and from there we will try to identify the data transformation behavior, right, by CNN based approach, and from there we will create the data leaders, okay, by visualizing the sample size of the sample image, and that's gonna give us some sample like that as an output, okay. And this is basically nothing but we will try to build up some kind of neural network or deep neural network. And then following that, we will also try to analyze the data set in the class distribution, and for that is going to give us the class distribution something like this, okay. And then we will try to build the CNN architecture by using the the PyTorch. Definitely we will try to do that. And further we will configure the training process and train the model. So once we train the model, we'll get something like that, okay. And then we will try to plot the training loss in that, like the plotting the training loss, we will get something like this. And then we will go for the evaluating the model accuracy. So once you do the model accuracy, you do the model prediction. So once you do the model prediction, you get the final output. So what I will ask all of you to kind of have a look into that, okay, and try to understand by using the PyTorch how it possibly work out, especially use some kind of CNN approach and how does it work, so that tomorrow we will have some idea to start with, and we will not be like everywhere, and then have some idea what to do, right? So then we will end the class here, and I will try to take some online question if you have any. If you have any online questions, you can just type your questions here. Other than that, I think I will see you all tomorrow. And if you have any other questions, you can also ask here if you have anything to ask. Okay, if not, then yeah, please go ahead.
for boundary rocks level, that is LP, can we calculate the uncertainty by citing an empirical relation with the data and the uncertainty is telling like
What kind of
AI
what kind of uncertainty quantification you are interested about?
If the AI is saying some different value